Welcome viewers to the second segment of the seventh lecture for the online series of lectures for the course of linear algebra. Towards the end of the previous segment, we stated Theorem 1 and proved it. Theorem 1 states that if V is a finite dimensional vector space over F and this is an ordered basis of the vector space V, so that V is n-dimensional, and W is a vector space over the same field F, and if W1, W2 all the way up to Wn are n vectors from the vector space W, defined over the same ground field F, then there is a unique linear transformation T from a V to W such that the following holds: T of Uj, these are all vectors, is equal to Wj for j belonging to this set 1, 2 all the way up to n. That is, for all j from 1 to n, T of Uj is going to be Wj. So the statement of the Theorem 1 guarantees the existence and uniqueness of such a linear map. Okay, so now we have an example elucidating this fact of Theorem 1, which we call example 4. In this example, we have two vectors, u1, whose coordinate matrix, this u1 vector is in this u1 vector and u2 vector are two given vectors in R2, and it is easy to check that these two vectors are linearly independent and since R2 is two-dimensional, these two vectors also span the vector space R2, and hence u1 comma u2 forms a basis for the vector space R2. In other words, this is a basis of R2. Okay. Now consider a second vector space R3. So in terms of Theorem 1, V is R2, and this is an ordered basis denoted by calligraphic B for the vector space R2. And in terms of Theorem 1, there is another vector space W which is R3, and now to translate things in for Theorem 1 in terms of this example, we need two vectors in the vector space W, which is R3 in this case. We choose those two vectors of R3 as 3, 2, 1 and 6, 5, 4. These two vectors are both in R3. So now, according to Theorem 1, there is a unique linear transformation T from R2 to R3 such that T of U1 vector is going to be equal to this vector 3, 2, 1. So this guy is W1 vector and this guy is W2 vector. if you want to align our notations with those of theorem 1 given in theorem 1, and then T of u1 is w1 and T of u2 is w2, which is 6 comma 5 comma 4, which is w2. So there exists a unique linear transformation guaranteed by theorem 1. What is that T? So we'll find this T in terms of its action on the standard basis vector epsilon 1, which is 1 comma 0. In other words, we are asking where does this epsilon 1 go under the action of T. In other words, what is T epsilon 1? Okay, all right. So in order to do that, we first need to write epsilon 1, the vector epsilon 1, which is 1 comma 0, as a linear combination of the basis vectors of R2. So in our case, the basis vectors are u1, which is 1 comma 2, and u2, which is 3 comma 4. Okay, so let us write this vector epsilon 1 as a linear combination of these two basis vectors c2 u2, so that we have 1 comma 0 to be equal to c1 times 1 comma 2 plus c2 times 3 comma 4, so that this is c1 plus 3c2, and the second component being 2c1 plus 4c2, so that we end up with a system of two linear equations in two unknowns, which is given by c1 plus 3c2 is equal to 1, and 2c1 plus 4c2 is equal to 0. This one is equal to 0. So we can easily solve it for c1 and c2, which gives us 2c2 to be equal to 2, which means that c2 is equal to 1, and c1 hence is equal to minus 2. Okay, so we have been able to write 1 comma 0 as a linear combination of the basis vectors, which looks like minus 2 u1 plus u2, right, plus u2, so that T of this vector 1 comma 0, according to the definition 4 in the proof of theorem 1, is equal to minus 2 times w1, right, which in our case w1 was equal to 3 comma 2 comma 1, and w2 is equal to 6 comma 5 comma 4. So minus 2 times 3 comma 2 comma 1, and 1 times 6 comma 5 comma 4. Okay, so it follows from the definition of T provided in equation 4. Let me check, it was indeed equation 4, right? In equation 4 of proof of theorem 1. Okay, so according to which this is minus 2 times 3 comma 2 comma 1 plus 1 times 6 comma 5 comma 4, which leaves us with minus 6 minus 4 minus 2 plus 6 comma 5 comma 4. This is 0 comma 1 comma 2. Okay, which means that the vector 1 comma 0 is mapped to 0 comma 1 comma 2 under the action of this unique linear map T. Okay, well, so that was example 4. Now we discussed two important subspaces that arise in the context of a linear transformation T between two vector spaces V and W defined over the same ground field F. Okay, one subspace is called range of T and the other subspace is called kernel of T. Okay, so kernel of T is also referred to as null space of the linear transformation T. So let me erase everything and define these two subspaces of interest. Okay, so given T, a linear transformation between these two vector spaces V and W over the same ground field F, we defined R sub T called the range of T as the set T acting on V for all V in the vector space V. Okay, so all possible images of the vectors in the domain vector space V, right, under the linear transformation T. The collection of all these images is called the range of T. And kernel of T is equal to the collection of all the vectors in the vector space V such that TV is nothing but the additive identity or the zero vector of the vector space W. Okay, so it is immediate that kernel of T is a subset of the vector space V and range of T is a subset of the vector space W. Now we will verify that these two subsets are actually subspaces of the respective vector spaces. Okay, all right. So in this case we are going to use theorem 1 of lecture 5, which we call subspace testing theorem. We use subspace testing theorem which is theorem 1 of lecture 5 to verify that these two subspaces are indeed these two subsets are indeed vector subspaces of the respective vector spaces. Okay, let us get started with range of T. Okay, so all we need to verify that given two vectors v1 v2 in range of T and a scalar C in the field CV1 plus V2 is also in RT. To verify that this subset RT of the vector space W is indeed a vector subspace. Okay, So let us start with this vector cv1 plus v2 and see where it goes under the action of this linear transformation T. So using the linearity of this transformation T, we write it as C T V1 plus T V2. Okay, and and since V1 is in range of this linear transformation T, there from the definition of this subset R sub T, there exists a vector U1, right? Well, no. There exists a vector, so right, okay. So we are choosing v1 and v2 to be two vectors in the range of T, right? So I think we don't need it at the moment, so let's cross it out. Okay, this part, something that we don't have to go over right now. Okay, so since v1 is in the range of T, there exists since v1 is in range of T, according to the definition of range of T, there exists a vector u1 in the vector space V such that T of u1 vector is equal to v1 vector. Okay, and right, and since v2 vector is also in the range, there exists a vector u2 in the vector space V such that T of u2 is equal to the vector v2. Okay, now I take so given these two vectors in vector space, I choose cu1 plus c2 sorry cu1 plus u2 is another vector in the vector space V such that T of cu1 plus u2 is equal to, right, C times tu1 plus tu2, right? This follows from the linearity of T since T is linear. Okay, so this is equal to, since T of u1 is equal to v1, this is C times v1 plus T of u2 is v2. So what have we found? So we have been able to show that we started with v1, v2, and arbitrary pair of vectors v1, v2 in the range of T, and any scalar C in the field F, there for v1, v2 in RT and C in F, there exists a vector C cu1 plus plus u2 in the vector space V such that T of cu1 plus u2 is equal to C times V1 plus V2. That is C times V1 plus V2 is also in the range of T. Okay, so we have been able to show that for a pair of vectors in Rt and any scalar C in F, CV1 plus V2 is also in Rt. Then by subspace testing theorem or theorem 1 of lecture 5, Rt is indeed a vector subspace of the codomain vector space W here. Okay, so now we need to show that the kernel of T is a vector subspace of this vector space V. Okay, so let me erase everything. So first of all, notice that T, remember the first remark of the first definition of linear transformation, that T maps the linear transformation map between the vector spaces V and W over the same ground field F, maps the zero vector of the vector space V to the zero vector of the vector space W, so that 0 sub V is in kernel of T, which means that kernel of T is a non-empty subset. There is always an element there in kernel of T. Now let U1 and U2 be two elements in kernel of T, so that from the definition of kernel of T, T of U1 is equal to the zero vector of the vector space W, and T of U2 is also the zero vector in the vector space W. So T of C times U1 plus U2 is equal to, by linearity of the transformation T, C times TU1 plus TU2. Okay, so now C is getting multiplied with the zero vector of the vector space W to give the zero vector in the vector space W plus the zero vector in the vector space W, which is the zero vector in the vector space W, which means that CU1 plus U2 is also in kernel of T. So we started with an arbitrary pair of elements in kernel of T, and we had an arbitrary field, arbitrary scalar C in the field F, and we have been able to show that C times U1 plus U2 is also in kernel of T. That means that by subspace testing theorem or theorem 1 of lecture 5, kernel of T is a subspace of the vector space V, is a subspace. Okay, good. Now, definition. Let V and W be vector spaces over the same ground field F, and we don't want them to be finite dimensional at this stage. And let T be a linear transformation from the vector space V to the vector space W. The null space of T is the set of all vectors U in the vector space V such that T of U is equal to the 0 vector of the vector space W. In other words, kernel of T is the same as the null space of T, as we mentioned earlier. Now, so this is the definition of the null space of the linear transformation T between these two vector spaces V and W. If now we want V to be finite dimensional. If V is finite dimensional, so we want the vector space V to be finite dimensional. For this definition, if V is finite dimensional, the rank of T is the dimension of the range of T, which is a vector subspace of this vector space W. Range of T, and the nullity of T is the dimension of the null space of the linear transformation T, is the dimension of the null space of T. Okay, so now we consider this linear transformation T from the finite dimensional vector space V to any vector space W over the same ground field F. The rank of T is the dimension of the vector subspace of W called range of T, and the nullity of the linear transformation T is called the dimension of the vector subspace, not vector subspace kernel of T, which is the vector subspace of V. Okay, so when V is finite dimensional, these two numbers are well defined: rank of T and nullity of T. Now, one of the most important theorems in linear algebra, which states that, relates these two numbers, rank of T and nullity of T. How they are related we find by means of this following theorem. Let V and W be vector spaces over the field F, and T from V to W be a linear transformation. Suppose V is finite dimensional. We need the domain vector space to be finite dimensional. Suppose V is finite dimensional, then rank of T plus nullity of T is equal to the dimension of the finite dimensional vector space V. Okay, so this theorem is called rank-nullity theorem. So we are going to prove this rank-nullity theorem now. So here goes the proof. Let U1, U2 all the way up to UK be a basis for kernel of T. Okay, we can talk about the basis of this subset kernel of T of the vector space V. Why? Because kernel of T is a subspace and V is finite dimensional, and we are choosing the dimension of this subspace of the finite dimensional vector space V to be K, and let this U1, U2 all the way up to UK be an ordered basis for kernel of T. The null space of T. Kernel of T is nothing but the null space of T, the same thing. Okay. So since kernel of T is a subspace, right, and this is a linearly independent subset in V, right? Kernel of T is a subspace, and is a linearly independent subset of V. And since V is finite dimensional, we choose the dimension of V to be n. We can extend this linearly independent subset to form a basis of the n-dimensional vector space V using lemma 1 of lecture 6. I guess it was lemma 1, the first lemma of lecture 6. Let me check. No, it's theorem 1. So we can extend it to form basis to form a basis extended to form a basis of the finite dimensional vector space V. Okay, and that we can do by corollary 2 to theorem 1 of lecture 6, previous lecture. Okay, all right, so we started with this ordered basis of kernel of T. Okay, first of all, T is a linear transformation between these two vector spaces. We suppose V is finite dimensional, and we choose the dimension of this vector space V to be n, and we know that kernel of T is a vector subspace of V, and since V is finite dimensional, its subspace is any of its its subspaces is finite dimensional, and we without loss of we choose the dimension of that vector subspace to be k, where k is strictly less than where k is less than n. Okay, and we then immediately see that this basis is a linearly independent subset of the vector space V, and we then extend it to a basis of the full vector space V in the following way: u1, u2, all the way up to uk, and then extend it to include these vectors k1, uk plus 2, all the way up to un. Okay, a basis. This is a basis of the vector space V. Good. So what do we need to show now? We will now prove that T uk plus 1, T uk plus 2, all the way up to T un is a basis of the range RT, the range of T. Okay, this is what we need to show. Now, first we try to see the following. We try to see that RT, the range of T, is equal to the span of these vectors T uk plus 1, T uk plus 2, all the way up to T un. So the span of this n minus k vectors is the range of T. That's what we need to see first. Okay. So given W in RT, there exists U in V from the definition of range of T, such that T of U is equal to W, right? This follows from the definition of range of a linear map. But since U1, U2, all the way up to UN is a basis for the vector space W, vector space V, we would always be able to write U as a linear combination of these basis vectors, which we do now. Sum of all these expressions Ci ui vector, where I runs from 1 to n, for some scalars Ci in the field. Okay, right, leading to so we just apply t on both sides to have t of u to be equal to sum of all the expressions Ci t ui vector, where I runs from 1 to n, and we can do that using linearity of the map T. Okay, therefore we have seen that given any vector w in the range of T, there exists scalars Ci in F such that W is equal to this sum Ci times T ui, where I runs from 1 to n, right? Okay, so we write it like this: C1 TU1 plus C2 TU2 plus Cn TUN. Okay, which means that this arbitrarily chosen vector from the range can be written as a linear combination of these vectors. Okay, and hence these n vectors span Rt. Okay, now remember that u1 u2 all the way up to uk was the basis of kernel of T. Okay, so all these numbers are 0, right? T of uj is equal to 0, where j is between 1 and k. So we can strengthen this result by excluding the first k vectors from here, because they are identically 0. So Rt is equal to span of these n minus k vectors, tuk plus 1, tuk plus 2, all the way up to tun. Okay, all right, so all right, good, we have come this far. Let me take a break, and in the third segment I will continue the proof from here. Thank you for attending the second segment.